Somewhere in our galaxy, there is a place where the laws of physics simply stop working. Scientists agree on almost everything about the universe, except what happens past this one boundary. Cross it, and there is no version of physics that lets you come back. Light itself, the fastest thing in existence, cannot escape once it gets too close. Every equation Einstein ever wrote breaks down completely at the center of this object. For over 2 centuries, scientists have argued about what is actually hiding inside it. In 2019, humanity captured a photograph of something we were told was unphotographable. That image confirmed something terrifying about the object at the heart of every galaxy. Yet even with real photographs now in hand, the true interior remains completely hidden. Some of the smartest physicists alive believe reality itself may not exist inside it. Others believe it could be a doorway, though not to anywhere we understand. There is a real scientific theory that says time behaves like space once you enter. That means falling toward the center might not be a choice you can refuse. Astronauts wouldn't just die inside one toward me. They would be stretched apart, atom by atom. Scientists actually have a real name for this horrifying process, and it is not fiction. NASA and the European Space Agency have spent decades building instruments just to study this. Nobel Prizes have been awarded for proving this object is really sitting at our galaxy's center. And still, after all of that evidence, no human has ever seen what's truly inside. What we're about to explain is backed by real data, real telescopes, and real physics. By the end, you'll understand exactly where science stops and mystery genuinely begin. In 1783, English clergyman and scientist John Michell proposed that some stars could be so massive that light couldn't escape them. He called these theoretical objects dark stars, reasoning purely from Isaac Newton's laws of gravity and motion. A few years later, French mathematician Pierre-Simon Laplace independently proposed a nearly identical idea using the same Newtonian logic. For over a century, this remained a strange mathematical curiosity, with no real evidence and no way to test it. Everything changed in 1915 when Albert Einstein published his general theory of relativity, redefining gravity itself. Einstein described gravity not as a force, but as the bending of space and time by mass and energy. His solution described an object so compact that space and time would fold in on themselves completely. Schwarzschild worked out this solution while serving on the Russian front during World War I. He died just months later, never knowing his equations would describe one of the most extreme objects in the universe. For decades, physicists, including Einstein himself, doubted these objects could actually exist in nature. They were treated as a mathematical oddity, a strange edge case, rather than a real astrophysical possibility. Still, the scientific community remained skeptical, and the idea sat largely unexplored for another 2 decades. It wasn't until 1967 that physicist John Wheeler popularized the now famous term black hole in a lecture. The name stuck instantly, capturing public imagination in a way collapsed star or dark star never had. In the early 1970s, astronomers found a powerful X-ray source called Cygnus X-1 in our own galaxy. Its behavior matched exactly what theory predicted for matter spiraling into an invisible, incredibly dense companion. Stephen Hawking famously made a private bet that Cygnus X-1 was not a black hole, and later conceded he'd lost. Through the 1970s and 1980s, evidence steadily accumulated that black holes weren't just math, but physical reality. In 1974, Hawking proposed that black holes weren't entirely black and could slowly emit radiation over time. Meanwhile, astronomers began tracking stars near the center of our own Milky Way galaxy with growing precision. Those stars appeared to orbit something completely invisible, yet millions of times more massive than our Sun. Decades of careful measurement by two separate research teams confirmed this invisible mass could only be a black hole.
In 2015, the LIGO Observatory detected gravitational waves for the first time, created by two colliding black holes.
That single detection confirmed a prediction Einstein had made exactly a century earlier, in 1915.
Then in 2019, the Event Horizon Telescope released the first-ever image of a black hole's silhouette.
Humanity had gone from a clergyman's guess in 1783 to an actual photograph in less than 2.5 centuries. So what exactly is a black hole, according to the physics we've confirmed through all of this evidence? At its simplest, it's a region where gravity has become so strong that nothing, not even light, can escape. The boundary marking this point of no return is called the event horizon, not a physical surface. Cross the event horizon, and every possible path through space now leads only toward the center. According to general relativity, gravity near this boundary becomes so intense that it warps time itself. From an outside observer's view, anything falling toward a black hole appears to slow down and freeze at the horizon. From the falling object's own perspective, however, it would cross the horizon in an instant, unaware anything happened. This strange mismatch is one of the most mind-bending confirmed consequences of Einstein's equations. Deeper inside, gravity grows so extreme that tidal forces begin stretching objects apart, a process called spaghettification. Near a small, stellar mass black hole, this stretching would be lethal long before reaching the center. Near a much larger supermassive black hole, however, the tidal forces at the horizon are actually far gentler. This means, in theory, a person could cross a supermassive black hole's horizon without immediately being torn apart. What lies at the very center is what Einstein's equations call a singularity, a point of predicted infinite density.
At the singularity, according to the mathematics, space and time curvature become infinite, and the equations simply fail.
Physicists are clear that infinite here isn't a real physical value, but a signal our theory has broken down. General relativity works beautifully everywhere except at this one extreme point, where it essentially stops making sense.
That breakdown is one of the biggest open problems in all of modern theoretical physics today.
What physicists actually need is a theory of quantum gravity, merging Einstein's relativity with quantum mechanics. No such theory has been confirmed yet, which means no one can say with certainty what truly happens at the center. This is the honest, current scientific answer. We know the boundary in extraordinary detail, but not the destination. Since no light or signal can escape a black hole, scientists can never observe its interior directly. Instead, researchers gather indirect evidence by studying how black holes affect everything around them.
X-ray telescopes detect superheated gas spiraling into black holes, glowing brightly just before it disappears forever.
This glowing material, called an accretion disk, is often how astronomers first identify a black hole's location. The LIGO and Virgo observatories detect gravitational waves, tiny ripples in space-time from colliding black holes. These ripples let scientists measure the mass, spin, and even the ring-down of a newly merged black hole.
That ring-down, the way space-time vibrates and settles afterward, closely matches Einstein's century-old predictions. In 2019, the Event Horizon Telescope combined data from 8 radio telescopes spanning the entire planet.
Together, they functioned as one telescope, roughly the size of Earth itself, to photograph a black hole's shadow. Their target was M87, a supermassive black hole sitting at the center of a galaxy 55 million light-years away. The resulting image showed a glowing ring of superheated material surrounding a dark, unmistakable void. That dark void was the black hole's shadow, the closest thing to an actual photograph of one ever taken.
In 2022, the same collaboration released an image of Sagittarius A, the black hole at our galaxy's center.
Both images matched Einstein's predicted shape almost perfectly, an extraordinary confirmation of century-old mathematics.
Researchers also study stars orbiting invisible masses to calculate exactly how heavy unseen black holes really are.
Some black holes are only a few times the mass of our Sun, formed from collapsing dying stars. Others, called supermassive black holes, contain the mass of millions or even billions of suns combined. How supermassive black holes grew so large, so early in the universe, remains an active area of research. Every piece of evidence gathered so far strongly supports the existence of the event horizon and singularity. But every single method described here studies the outside of a black hole, never the inside itself. So here is the honest reveal. No human observation has ever confirmed what physically exists past the horizon. Everything beyond that boundary is, right now, mathematical prediction rather than directly observed physical fact. General relativity predicts a singularity, but most physicists suspect that prediction isn't the final, complete answer. One hypothesis, called the fuzzball model, suggests there's no true singularity, just an extremely dense, fuzzy quantum structure. Another idea, the firewall hypothesis, suggests infalling matter might hit a wall of extreme energy at the horizon itself. Mathematically, Einstein's equations also allow for something called an Einstein-Rosen bridge, popularly known as a wormhole.
This is a real mathematical solution, but there is currently zero physical evidence that traversable wormholes actually exist.
No black hole ever observed has been confirmed to lead anywhere, to another universe or otherwise. There's also the black hole information paradox, one of the most serious unsolved problems in modern physics. If Hawking radiation causes black holes to eventually evaporate, what happens to the information that fell inside? Quantum mechanics says information can never truly be destroyed. But general relativity seems to say otherwise. This direct contradiction between two of physics' most trusted theories remains completely unresolved to this day. Some physicists, including Hawking himself later in his career, proposed information could leak out in subtle, scrambled forms. Recent theoretical work involving quantum extremal surfaces has offered promising mathematical progress, but no final consensus exists. What all of this means is simple. The deepest interior of a black hole is genuinely unknown territory. It isn't unknown because scientists haven't looked hard enough. It's unknown because it may be unknowable with current physics. Event horizon acts as nature's own privacy wall, permanently sealing its secrets from outside observation. Even theoretically, information can only ever fall inward, never travel back out to tell us what it found. This is why physicists describe the singularity as the edge of known physics, not just the edge of space. Everything past that edge waits on a future theory that doesn't fully exist yet. So what is actually inside a black hole, according to everything we've just walked through together? Confirmed fact, there is an event horizon, a boundary beyond which nothing, including light, can return. Confirmed fact, matter falling inward experiences extreme time dilation and, closer in, violent tidal stretching.
Scientific theory, strongly supported by evidence. General relativity accurately predicts the black hole's outer structure and behavior.
Scientific theory, less certain. A singularity of infinite density exists at the exact center, per unmodified relativity. Scientific hypothesis, unconfirmed. Alternatives like fuzzballs, firewalls, or quantum cores may replace that classical singularity entirely.
Scientific hypothesis, largely unsupported. Wormholes or connections to other universes, mathematically allowed but never observed.
Future mission goal. Physicists hope next-generation instruments will test these competing ideas more precisely than ever before.
The planned next-generation Event Horizon Telescope aims to capture sharper images and even black hole video.
The European Space Agency and NASA are developing LISA, a space-based observatory to detect gravitational waves in space.
LISA is designed to detect black hole mergers, and current ground-based detectors like LIGO simply cannot see. These future tools won't show us the literal inside, but they will test our theories more rigorously than ever. That's ultimately how black hole science moves forward, not through direct sight, but through relentless, indirect testing. Every prediction that survives scrutiny brings us one step closer to understanding what waits beyond the horizon. Every prediction that fails helps physicists rule out ideas and refine the search for a true theory of quantum gravity. This is the same slow, careful process that took humanity from Michel's 1783 guess to real photographs today. It's worth remembering that black holes were dismissed as unlikely fiction for nearly 2 centuries. Then, piece by piece, indirect evidence turned a mathematical oddity into one of astrophysics' best confirmed phenomena.
The same could eventually happen to our current guesses about the deepest interior, the singularity itself.
Perhaps within our lifetimes, a real theory of quantum gravity will finally replace speculation with genuine understanding.
Or perhaps this is one mystery that remains permanently beyond direct human observation, by nature's own design. Either way, the honesty of not knowing is itself one of the most important parts of real science.
It would be easy to invent a confident, dramatic answer about black hole interiors for the sake of a good story. But actual science requires separating confirmed evidence from elegant theory, and elegant theory from pure speculation. What we know for certain is already strange enough. Gravity that stops light, time that stretches, matter that stretches too. What we don't know is stranger still. A place where our best equations simply run out of answers. Every galaxy we've ever studied appears to have a supermassive black hole quietly anchoring its very center. That includes our own Milky Way, orbiting a black hole we now have real, confirmed images of. In some sense, every one of us has always been circling one of the universe's greatest unsolved mysteries. Somewhere out there, matter is falling past an event horizon at this very moment, disappearing from our observable universe. But that matter experiences, physically, remains one of the last true frontiers of scientific discovery.
Solving it won't just satisfy curiosity. It may finally reveal how gravity and quantum mechanics truly connect.
That single breakthrough could reshape our entire understanding of space, time, and the structure of reality itself. Until then, black holes remain what they've always been, nature's ultimate, elegant, unsolved question.
Not a monster to fear, but a boundary that marks the very edge of human knowledge.
Every photograph, every gravitational wave, every orbiting star brings that boundary a little closer to us.
But the true answer, what genuinely happens at the deepest point, still belongs to the future. Somewhere between Einstein's equations and tomorrow's unwritten theory of quantum gravity, that answer is waiting.
For now, the most honest thing science can say is also the most fascinating thing it can say. We don't fully know yet, and in a universe this vast, that single unanswered question might be the most exciting discovery still waiting to happen.